Hello and welcome to this taster lecture. My name is Elenia Creda. I'm an assistant professor in computer science in Durham, and today we're going to talk about map and graph coloring. I presume you're familiar with how we color maps in general in a way that neighboring regions of the map are distinguished by using different colors. For example, here you've got an uncolored map of the United States of America, and here you have a multicolored version so that states that share a border have different colors. Now, taking a step back and looking at problems in computer science and natural sciences in general, our aim is to solve real-world problems, but the way we do it is we actually rephrase the problem we're looking at as an abstract problem. We remove all the unnecessary details that we don't really need in order to find a solution, and then for this abstract problem we try different solutions until we find a good one, which we then translate in terms of the original problem. It's often the case that the abstract model that we create from the original problem involves some sort of graph or network. Now, when I'm talking about graphs, I'm talking about pairs of a set of vertices and a set of edges, where an edge itself is a pair of vertices, which indicates some form of connection between those two vertices. For example, suppose we want to define a graph G1 with 4 vertices and 3 edges like so. So 1, 2, 2, 3, and 3, 4. We can actually visualize graphs, and it's much easier to understand their structure by drawing points as vertices and lines as the edges. So here, this edge 1, 2 corresponds to this line here. And what you can see here is what we call the 3 path. It's just a line of 3 edges. Notice, however, that it doesn't really matter how you draw the 3 path, whether it's like so or in any of these ways. It's the edges that count. So it doesn't really matter how we draw the graph as long as the edge set remains intact. Now on to a special class of graphs, which we call planar graphs, which are graphs that can be drawn on the plane so that no edges cross each other. And these are a special type of graphs because every map can translate into a planar graph and vice versa. So to translate a map into a graph, you take each region of the map and you define a vertex for that region. And then for any 2 regions that share a border, you create an edge. So keeping that in mind, look at this example here. This is a partial European map. We have some countries as our regions. So if you look at the corresponding planar graph, hopefully you'll realize that this vertex here, which has 7 neighboring vertices, is actually a vertex corresponding to Austria, which has 7 countries that it shares a border with, each one of which shares a border with another 2 out of the 7. Plus, we also have Poland, which shares a border with Germany, the Czech Republic, and Slovakia. So Poland, with 3 neighboring countries, would be this vertex here. So take a minute maybe to understand the connection between the 2. And once you do that, I then want you to look at a different graph, this one, and try to see if you can figure out whether this graph is planar or not. So can it be drawn on the plane so that we don't have this here? We don't have any 2 edges crossing each other. So maybe pause the video for a second. Hopefully you've done that and you've got the answer, which should be that this graph is indeed planar because you can redraw it like so that no 2 edges cross at any different point other than obviously a vertex, which will happen. Now think of the original problem that I mentioned. We've got maps and we want to color them using different colors to distinguish countries or regions that share a border. Now the problem now is, how can we do that using as few colors as possible? This is a very natural problem, right? It's actually been stated since 1852. It's a very famous problem, which was then transformed into a theorem, the four-color theorem, that says that you can color any map in such a way using at most 4 colors. And I dare you to try any map. You can color it using 4 colors at most, so that no two neighboring regions share a border. This problem has got a very long history with attempts to prove it. Unfortunately, none of them were successful until finally 1976, when it was proven, and it was the first proof done by computer. This is here an example of a 4-colored version of the USA map. And maybe you're sitting there thinking, oh my God, who cares about graph coloring? Many people actually care about graph coloring because many real-world problems translate into the problem of finding the chromatic number of a graph, meaning the smallest number of colors needed to properly color a graph. Properly meaning you color the vertices of the graph so that no two neighboring vertices have the same color. It's like coloring the map so that no two neighboring regions have the same color. So the same problem, but in terms of graphs rather than maps. And indeed, there are various applications of the graph coloring problem, finding the chromatic number of a graph, from scheduling problems, exam timetabling, and what have you, to even solving Sudoku puzzles. It's actually the case that for some special classes of graphs, it's easy to compute the chromatic numbers. So when your graph is a path, no matter its length, whether it's a 3 path or a 110 path or 1,000 path, the chromatic number is always what? Have a little think. The chromatic number is always 2. You can always alternate between 2 colors, and that way you will color all the vertices of the graph, of the path, so that no two neighbors share a color. On the other hand, when your graph is what we call a complete graph, so every vertex is connected to every other vertex with an edge, then how many colors do you need to color this graph properly, so that no two neighbors share a color? Hopefully you've got the answer by now. The answer should be as many colors as the number of vertices. So here you've got 1, 2, 4, 6 vertices. You need to have 6 different colors in order to say that you've properly colored this graph. So maybe now take a minute, maybe pause your video and try to copy these graphs onto a piece of paper and try to figure out what the chromatic number of each of these graphs is. So the smallest number of colors that you need to color the vertices so that no two neighboring vertices share a color. Hopefully you've paused the video and hopefully you've found the solution to the exercise. You should have found that the chromatic number of this graph is 2. This graph is 4 and this graph is 3. The essence of this exercise was just to show you that it's not always straightforward or even easy to compute the chromatic number of a graph. And it's actually, in general, it seems to be a computationally very hard problem. And in fact, which also goes to show that people do care about graph coloring enough, in fact, if you do manage to find, you or anyone else manages to find a quick algorithm, a quick method to answer what the chromatic number of any given graph is, then you will earn yourselves $1 million. It's actually, this problem is actually one of the Millennium Prize problems. So it must be a quite important problem for it to have such a reward if you solve it. So what I would like to do now is thank you for your attention so far, and maybe urge you to visit our website, where you can find out more about the programs that we offer and the modules that we offer, some of which do contain parts of what we've talked about today. Thank you.